Okay, so 10.7 is essentially an introduction to this idea of polar coordinates. So I'm just asking you to review first with 10.6, finding two sets of parametric equations with opposite orientation for y equals 2 minus x. So that means, can we graph this line, 2 minus x, but like moving in a different direction, right? As t changes, or as we set different parameters, we could increase versus decrease, or something along those lines. So when I looked at this problem, I said, well, let me just graph the line first. Whoops. 2 minus x has a y-intercept of 2, slope of -1, simple. If I came up with my xy ordered pairs as a normal rectangular graph, right, I would just have, if x is -2, y is 4, x is -1, y is 3, 0, 2, 1, 1, 2, 0, and so forth from there. Okay, so what's going to just change the orientation? There's not much I can do, right? I can't go crazy because then it would change the line. I have to maintain this exact same equation, same graph. So I said, well, what if we just messed with the positive and the negative a little bit, right? So what if we said, let x equal -t versus x equaling positive t. If x equals -t, then y equaling 2 plus t would give me that same line, right? But it would work in a different direction than x equaling t, because then y equals the same, 2 minus t. So this one would graph in the same way that I just did those ordered pairs, right? I could add my normal t in here as the same exact values, and therefore as I move, I would go that way, right? As t increases, my y's are decreasing. But if I looked at this one, I have to make a whole new table, I think. I can't just throw it in there. I would have to throw it in the reverse direction, so I don't want to do that. All right, let's say that if x equals -t, so then if we had the same xy axis, and we threw in our t's, or t equaling -x would be the other way to think about that, right? So if I threw in t's of -2, -1, 0, 1, and 2, my x's for this equation are 2, 1, 0, -1, -2. Okay, with that? My y's are 2 plus -2, or 0, 2 plus -1, or 1, 2 plus 0, or 2, 2 plus 1, 3, 2 plus 2, 4. So it's not that I end up with different ordered pairs, but now it's saying as t is -2, and I move across, like the first point that I plot would be this would be this positive 2, 0. Let me just change. Then I would plot 1, 1. Then I would plot 0, 2. Then I would plot -1, 3. Then I would plot -2, 4. So my direction, my orientation, goes the other way by a simple sign change. Not changing the equation, not changing the line, but the orientation. the warm-up for 10.7 is a little unit circle review. So I know on Zoom it's hard to call out. Sorry, I'm going to turn my computer again so you can actually see me. But, I don't want to fill these in for you. So what is sine of pi over 4? Anybody? Something is 1 at pi over root 2 over 2. So tan is 1 there. Yes. Let's go down. So cosine at pi over 3. Cosine at 60. 1/2 is correct. Cosine at pi. -1. Sine at pi over 3. Sine at pi over 6. Tan at pi over 4. 1. Tan at 0. 0, right? Sine over cosine is 0. Tan at pi. Cos at pi over 6. 3 over 2. Quick thing for you all, right? Full disclosure here. I am a AP calculus teacher. I have never taught pre-calculus until currently. I, therefore, didn't get into the whole teaching of memorization and tricks and all of these things because it is what it is. I took pre-calc Excel when I was a sophomore at this high school and didn't have a good experience. It was what it was. We won't get into that. It was not a teacher that is currently here, so I can say that as openly as I want to. But I'm going to move on from that. Let me stop recording. All right. Graphs of polar coordinates are very pretty, right? Butterfly. There's a ton of very popular polar curves out there. We'll just get into a glimpse of them. We'll get into how to graph in polar coordinates, how to convert back and forth. But there's a ton of things, ton of applications for mapping out these polar graphs. And you absolutely will see this more in Calc if you're in Calc BC next year. It comes up a ton. Just like parametrics, the direction and the orientation of things is important. Like we move around the graph counterclockwise like we do in the unit circle when we plot points. We use the polar coordinate system. We're not using rectangular anymore. So what we know as the x-axis is sort of like we have a radius going, concentric circles, different size radii, and we have our angles going around the whole thing counterclockwise. Okay? So depending on the curve and depending on how we go, understanding that everything has curve to it, it's not going to be linear, and the direction that we map it out is obviously going to be important. So again, these are just other references to famous and also some common polar graphs. So this one is talking about how a microphone picks up sound pattern, which is pretty interesting. So read it when you have some time. Some of this stuff is referenced in the textbook as well. So here's where we get into some of the stuff that we're going to cover in pre-calc Excel. First of all, being able to convert and plot points in polar coordinates. Your polar coordinate will always be in the format of r, comma, theta. R tells you what radius of a circle you're on. Theta tells you where to go as you rotate around. Right? You're always rotating counterclockwise. Rectangular coordinates are distinct. Yeah, that's the word I'm looking for, right? They are individuals. One can't be the other, right? X comma y is its own ordered pair. Whereas, because of the nature of a rotation, r comma theta could have other equivalent r comma thetas. You can add 2 pi n to your theta or subtract it, or add 4 or 6, etc. And you would still have the same exact point because all you're doing is going around in a circle, a full rotation, getting right back to where you started with. You can also negate your radius and then add an odd pi and get back to where you started with, or subtract an odd pi and get back to where you started with. Okay, so they're not unique. When I think about R, I think a little bit of direction, but it's not what we do with our x. When we get our x coordinate, if it's positive, we move to the right on the number line. If it's negative, we move to the left on the number line. It's a little different than that. I plot my R second. Think about the angle that I'm at. I go to that angle. So it could be negative pi over 4, I'm heading down that way. If I'm at negative pi over 4 and my R is positive 2, I go down there and plot my point on that concentric circle. If R is negative 2, I walk backwards. I travel backwards over to here. So that's kind of I think the hardest part of how does R put me over here, you know? So that's going to be the challenge. It's not quadrants 1, 2, 3, and 4 anymore. It's not X's left or right. It's a circle, and you're moving counterclockwise. There's multiple angles that will put you at the same place. R can be positive or negative, and it's all about the directed distance from the origin to that point P. Okay, so let's first plot these points and find two additional polar representations of the point. And we're not going to reach my goal. Let me start by plotting these points. We'll pick up here first thing on Friday where we'll actually come up with equivalents, okay? So if I'm plotting 3 comma negative pi over 3, I start at the origin, of course. When I think about negative pi over 3, it's right here. I'm sorry, it's not right there. That's pi over 6. It is the next one, right here. Right? So 3 would be 1, 2, third circle out. That would be my point A. B, positive pi over 6, and the R is 2. So I'm here. I go pi over 6 is my angle, second circle, second radius. Last one, the angle is a positive pi over 4, which is not always plotted on these, so that's here. But it's a negative 1, so I walk backwards to that first circle, point C. I walk in the opposite direction. We'll plot more and more of these, but again, this is my pi over 4 angle. My radius was negative, so I plot my point in the opposite direction. Okay? I'm going to pause. So after we see how we have A, B, and C plotted, with point A, if we choose to keep the R the same thing, how do you think we can manipulate the theta so that we end up at the same exact location again? What would we do? Like, give me an equivalent form. We could add 2 pi's, exactly. That's all I want to notate right here, is that we can add 2 pi's, or if I negate my R, what could I do there? What's that? Add just a pi, yep, or subtract just a pi, either way. Cool. Same idea with B, right? If I keep my 2, I can add 2 pi to pi over 6 and end up at the same exact location. Or if I negate my 2, right, this time I'll write it as a plus pi. That would be another option. Doesn't matter. So let's just test it really quickly. So here I'm at 7 pi over 6, right? Negative 2 comma 7 pi over 6 is the example I want to test out, point B. So 7 pi over 6 would be over here, right, on the unit circle. But because I have to have a negative r, that's when I say to myself, all right, I walk backwards to that circle, and I get back to the point B that's exactly there. So even though I'm on this line creating the 7 pi over 6 angle from the origin, from 7 pi over 6, I walk backwards and I get back to B because the r was negative there. Negative 1 comma pi over 4 could go negative 1 comma pi over 4 plus a 2 pi, or positive 1 pi over 4 plus a pi. So same idea if I wanted to test this out with point C. With my pi over 4 angle, right, I put that in the red line, then I walk backwards to get to C because it was a negative 1 radius. So if I do a 5 pi over 4, well, I go around counterclockwise until I get to 5 pi over 4, and my radius is a positive 1 there. So I'd go in that direction. Okay? So those are all equivalent forms for the same point. We want to be able to convert we want to be able to convert from polar to rectangular, as well as from rectangular back to polar. So these are some equations that are going to be really helpful in this process. It all, again, is based on unit circle and our right triangles in that unit circle. The r is our radius, the r comma theta is the point, as well as x comma y. So to have something equivalent, x would be equal to r cos theta, y is equal to r sine theta, because, right, from our triangle, sine theta was equal to y over r, right, or opposite over hypotenuse. Cosine theta was equal to x over r, or adjacent over hypotenuse. And tan is your y over your x. So therefore, these relationships are just manipulated to get to those two. Right? The tangent theta, because it doesn't include an r, that is helpful in converting rectangular to polar. And then the r squared equaling x squared plus y squared, which is our Pythagorean without the square root, is helpful in converting as well. Okay? So those are some relationships that we will be using. So these examples, we want to convert to rectangular coordinates if we're given 4 comma pi over 2. So that's r comma theta. So if we want to do that, well, we're kind of putting in our minds that x is r cos theta, y is r sine theta. Right? So x would then be equal to 4 cosine at pi over 2. Cosine at pi over 2 is what? 0. So then it's just 0 for that coordinate. Y is equal to 4 sine at pi over 2. So we get a 4. Which puts us, like if we think about that, pi over 2 would be the angle that's going directly up. Positive 4, so we're up there at that radius on our polar graph. And then if I plot it in rectangular, the same thing, it would be in that same exact location. Okay? 2 comma pi over 6. So same idea here. We just say x is equal to 2 cos at pi over 6. Cos at pi over 6 is equal to root 3 over 2. So 2 times root 3 over 2 would just give us a root 3. Y equals 2 sine at pi over 6. So sine would be the 1/2. 2 times the 1/2, we get a 1. Root 3 comma 1. That's okay. Converting to polar coordinates. So here's where we're going to start with our tangent theta equaling y over x. That will then tell us what our theta is, right? So we can say tangent theta in this case equals 2 over 2, or 1. So theta must be pi over 4. We do want to acknowledge that 2, 2 is in the first quadrant, so it makes sense to choose pi over 4 because there certainly could be a different angle that we would choose based on the quadrant that we're in. All right, but pi over 4 makes sense. So then we can say, in order to figure out what our r is, r squared equals 2 squared plus 2 squared, or r is going to equal, if we simplified that, root 8, or 2 root 2. So this ordered pair, or this polar coordinate, is 2 root 2 comma pi over 4. Questions so far? Good. All right, last one, -1, 0. All right, so tan theta equals 0 over -1, which is 0. Okay. We think about where that's located, right? It's 0, so we do want to know, well, what angle gives us that, but the x-coordinate is a -1 right now. Right, so theta being 0 wouldn't make sense, but theta being pi is what we would want, right? Then we say r squared equals -1 squared plus 0 squared. So r equals 1. So 1 comma pi would graph that same point of -1, 0. In the notes, the next page are just some included, actually the next 2 pages are just some grids for you. Okay, so you can always kind of pull this up if you need to when you're graphing. This one, like most of them, just have it, they all do have it broken up with your pi over 3, 6s, 2s, etc. They don't have the 4s. I'm not sure why they don't have pi over 4s, but they don't. Oh, this one does. This one's broken up more for you. Okay, good. So if you need those, grab them, whatever. Now, how about equation conversion? So not only can you replace or convert from point to point, you can do the entire equation. So here we are in rectangular form, and we want to bring it to polar. So again, recalling that that y equals, is what I meant to write, r cos theta, and x equals r sine theta. Oops, I wrote that backwards. X equals r cos, and y equals r sine. Okay. Some of these can be more challenging than others, for sure. When you're going from rectangular to polar, I find them easier because it starts with substitution. And from there, we manipulate things and we try to use identities where necessary, and otherwise it just kind of is what it is. So what I mean by that, in this case, y is r sine theta. So I'm just going to replace my y with r sine theta. X is r cos theta. So I'm doing the same thing there, and I have a squared. All right. Now what I want to try to do is solve it so it says r equals blank. Okay? So I have r sine theta equaling r squared cosine squared theta. I can divide by an r. So sine theta equals r cosine squared theta. And then I can isolate my r. So I would have r equals sine theta divided by cosine squared theta, which I could simplify a little bit more, because if I have a sine, if I split my cosine squareds, sine over a cosine, I have a cotan, and then a 1 over a cosine. I'm sorry, sine over cosine, I have a tan. And 1 over cosine, I have a secant. So I could write it like that. I'm okay with leaving it, because there's going to be times when you can't simplify it. Is it wrong? It's not wrong. If it's something that's relatively easy to simplify, you should out of good practice. But for my grading purposes, I'm going to say that's not a big deal. But again, if it were multiple choice, at least being able to recognize that they're equivalent would be important. I'm trying to answer this question based on what you're going to see next year, right? And they're fine. Both are fine. Okay. Okay. So 2xy equaling 1. Okay. Replace them. So 2 times r cos theta r sine theta equals 1. And then we just work to isolate our r. So we have 2r squared cosine theta sine theta equaling 1. So if I divide by the 2 cosine theta sine theta, I have r squared equaling 1 over 2 cos theta sine theta. Square root it. So this is another example where that answer is acceptable to me, but we could acknowledge that 2 cos theta sine theta is equal to sine 2 theta. Both are fine. I know I'm moving a little bit fast, but again, this will be recorded and posted, so you can always slow me down. But I want to get through all of the examples. So polar to rectangular. Describe the graph, then find the rectangular equation. So r equals 1. R equals 1. Literally, that just means it is a circle centered at the origin that has a radius of 1. There's nothing else to it. So no matter, it's like saying, no matter what the theta is, r is going to be 1. Kind of like when you're graphing a horizontal or a vertical line in rectangulars, when you get like x is 2. You're like, oh, well, what do I do with that? Well, it just means I don't care what y is. X is always 2. I get a vertical line. In polar, if there's no theta involved, then you just have a circle. It doesn't matter what angle you're at. It's always going to map around that circle with a radius 1. Okay, then if we want to convert this, remembering that x squared plus y squared equals r squared. R is 1, so therefore x squared plus y squared equals 1 squared. That in rectangular form is our formula, is a circle centered at 0, 0. Right? Same exact thing. next example. Theta equals pi over 4. Again, you're like, all right, how do I graph something like this? Similar, if I had a y equals 2, I would have a horizontal line. I don't care what x is, this is what y is. I don't care what r is, this is what theta is. So theta being pi over 4 is the line that creates the angle of pi over 4. Okay, so if we want to convert this now to rectangular, the x squared plus y squared equals r squared is not helpful, but the relationship of tangent theta equaling y over x is. Because if I have a theta, well, tangent at pi over 4, that's 1, right? Tangent at pi over 4, or tan theta, that equals y over x. So I can jump from here to here and say, well, y over x equals 1. So y equals x. And wouldn't that also be the line that goes through the origin with a slope of 1? Right, just like a 45-degree angled triangle, you know, the base and the height are the same. So the slope is the same. The slope is 1. Okay, here's one that actually includes r and theta. This one's a little bit harder to think about graphically in this form. Let's convert it first and see what we get. So, again, keeping in mind, if I want to go to rectangular from polar, all of my relationships are going to be helpful, right? If I can find an r cos theta, then I have an x. If I can find an r sine theta, then I have a y. If tangent theta is coming up, I have a y over x. So each problem I have to kind of look at it a little bit differently, just like your stuff in, I think it's chapter 6, at least it was with the old book, all of your trig identities. So here, what if I tried dividing by a cosecant theta on both sides? Well, cosecant is the same as, yeah. So then this is really r sine theta equaling 1, right? Well, r sine theta is y, right? So y is just 1. When you're converting, you're looking to get rid of the r and the theta, because rectangular doesn't have either of those. They have x's and y's. Y equals 1 is our horizontal line at 1. So sure, it touches the top of that circle, and if I plotted that point, they would definitely have that in common, along with all of the others. That would just be the easiest one to find. Good luck, Akshay. Okay, I am going to leave this problem. I'm not going to put it in the video. It's I think it's one of the homework problem sets. If it's not, it's one that I want to go through. I'm just kind of giving you the preface that it's not an easy one to convert. They're not all going to be obvious and easy. This one in particular is a challenge. I want to bring us back to it on Tuesday when we see each other in class before we get into 10.8 notes. Okay?